Hello, in this video I want to go through this guided worksheet on hydrogen bonding, polarity, and water solubility. Hopefully this video and your notes that you're going to take will help you with the pre-lab assignment. This semester it happens to be on green paper, and the pre-lab assignment deals with also hydrogen bonding, polarity, and water solubility. In a different video, I'll talk about answering questions about stoichiometry tables and equivalence. That would be part 2. But this video is just for the hydrogen bonding, polarity, and water solubility part. For hydrogen bonding, we know that as a very specific type of dipole-dipole intermolecular attractive force. So how molecules are held together. A lot of you may be familiar with DNA base pairing. So for instance, here we have 3 hydrogen bonds designated with a dotted line between guanine and cytosine. Why are these attractions taking place? If you take a look at the same 2 base pairs and put your partial charges, you will see that opposites attract. For instance, here we have a partial positive hydrogen. It's going to be attracted to a partial negative oxygen. And you could draw a dotted line like this. So again, if you draw in your lone pairs and your partial charges, you could identify these possible hydrogen bonds. Now, the skill to do something like this is pretty simple. So we're going to mark the partial positive and partial negatives so we can find the opposites that are attracted to each other. Basically, the partial negative atoms will be the electronegative atoms. And if you think about the periodic table, on the second period you have NO F, and then going down the column of the halogens you have F, Cl, Br, and I. So those are all considered electronegative atoms. You find one of those in your molecule, most likely it will be okay to put a partial negative. Now, the one exception that I could think of is if you have a nitrogen-nitrogen bond, and so that bond would be non-covalent because you're bonding to the same atoms. But in this example, we have nitrogen either bonded to hydrogen or carbon. We have oxygen bonded either to carbon and, well, we don't have an example, but you know that oxygen can also bond to hydrogen. So find all of these electronegative atoms and put a partial negative. Now, other atoms that can also have a partial negative will be the atom underneath nitrogen, which is phosphorus, and the atom underneath oxygen on the periodic table, which is sulfur. Okay? The next thing is, what about your partial positives? So any atom connected to an electronegative atom will be rendered partial positive because that electronegative atom is pulling electrons away from that atom that's going to be partial positive. So for instance, we have a nitrogen here, automatically put a partial negative, and then any atom attached to that nitrogen should be partial positive because nitrogen is pulling electrons away from that carbon, away from this hydrogen, and away from this carbon here. And that's how we're going to identify, right, these bonds that are polar bonds. We're going to talk about water solubility a bit later, but that has a potential for hydrogen bonding as well. And we have this one here, partial positive hydrogen, partial negative oxygen. Okay, so some more specifics. Once you get the partial charges on your molecules and the lone pairs, what is a hydrogen bond specifically? It's a dipole-dipole interaction between 2 or more molecules. And what is required? What is required for these hydrogen bonds to take place? Here's another one. Okay, 3 hydrogen bonds for guanine and cytosine. Well, one of the molecules we're going to call a hydrogen bond donor, and it has a hydrogen covalently bonded to an N, O, or F. Very specific. So hydrogen bond, the hydrogen that's involved in the bond has to be connected covalently to N, O, or F. So if we take a look at this hydrogen right here, right, that's the hydrogen donor because it's connected to an N. So that's covalent, right? This is your covalent bond. That's one of the partners. And so that would be the donor because we're using its hydrogen to make the hydrogen bond. And it's partnering up with another molecule called the hydrogen bond acceptor, and it has an electronegative atom that is attracted to that hydrogen. So here's your partial positive, and here's your partial negative. Okay. So again, for your hydrogen bond, you need a hydrogen bond donor, which has the hydrogen covalently attached to N, or O, or F. I don't have those examples here. Maybe on the next page I do. And then the acceptor is the electronegative atom that is attracted to the partial positive hydrogen. Now that electronegative atom could be any electronegative atom. For it to be a hydrogen bond, it's really important that this be the one that's covalently attached, that it be nitrogen, oxygen, or fluorine. These are pretty electronegative, these three here. So they really make that hydrogen partial positive. So, can we identify the hydrogen bond donor and acceptors in this guanine cytosine base pairing? So here I have bond 1, 2, and 3, hydrogen bond. And so for number 1, do you see how the hydrogen bond donor is the cytosine? And the acceptor, the one accepting this hydrogen through the hydrogen bond, is this oxygen, electronegative oxygen, that's part of guanine. In number 2, we have the opposite. Do you see how the hydrogen bond donor now is the guanine? Because it's covalently attached to the nitrogen of guanine. So that's the donor. And here's your nitrogen, electronegative atom, that is accepting this hydrogen in this hydrogen bond. So the acceptor in this case is cytosine. So you can identify per hydrogen bond who is the donor and who's the acceptor. Over here, see how the hydrogen is being sort of contributed by the guanine, and it's being accepted by the oxygen of the cytosine. Okay, so hopefully you can see hydrogen bond donors and acceptors. When we talk about the organic chemistry lab, typically we're going to talk about organic molecules and solvent. And so here, we're not going to go through this. You'll do this on your own and hopefully with your study group. So here I have several dotted lines. Not all of them are hydrogen bonds. I probably said here, for each dotted line, identify whether you have a hydrogen bond or a dipole-dipole attraction. Remember the hydrogen bond, right? Those are your requirements, right? It also says here, if you have a hydrogen bond, figure out who's the hydrogen bond donor and who's the acceptor. Alright, so that's all I want to say about that problem and about hydrogen bonding. Let's take a look at page 2. Oh, actually there's more hydrogen bonding here. So here's a possible assessment or quiz question or problem. Draw several ways the amino acid serine, this is serine, can hydrogen bond to the TLC plate. Okay, so again, we need a hydrogen attached covalently to oxygen, nitrogen, or fluorine. So here's one attached to oxygen, and here's an oxygen, and we know that that is electronegative. So here's one possible hydrogen bond. Understood? Here we have an electronegative atom, and here we have a hydrogen connected to O. So here's your donor, here's your partial positive, and here's your partial negative. And so I'm only labeling the partial charges on the atoms that are participating in the hydrogen bond. Oh, here's a potential hydrogen bond. Here's the donor, and here's the acceptor, possible acceptor, or even this oxygen. And you just want to double check. You know that the oxygen's partial negative, and this hydrogen's partial positive because it's next to a nitrogen that's pulling electrons away from it. Okay, you can do this one on your own. I just flipped the molecule because I want to see if there's hydrogen bonding with this OH group. So I flipped it so it's closer to the TLC plate. Now, just a disclaimer, if you've worked with amino acids a lot in the past, you might know that actually it doesn't exist like this in the fully neutral state where every atom is neutral. In water, amino acids tend to become charged. And so serine actually exists like this in water. But I wanted to use the fully neutral molecule to show hydrogen bonding to a TLC plate. But in solution, especially water, it would look like this. And I mean, we would still have hydrogen bonding per se, like with this hydrogen here as the donor, or possibly this hydrogen also as a donor. But I don't want to show ion dipole interactions. I wanted to show dipole-dipole interactions, which are hydrogen bond is a part of the dipole-dipole interaction family. I hope that didn't confuse you too much. But yeah, you could get ion, right? These are ions now. These are not dipoles. And I didn't want to show ion dipole interactions. I just wanted to show strictly hydrogen bonding interactions. Okay, next issue. Now that we've looked at partial charges and formal charges in this case, does that affect polarity? And well, how does polarity and water solubility go hand in hand? In organic chemistry, for the most part, the more polar a molecule is, the more water soluble it is. And we need to know water solubility because when you run a reaction, you want to know, is your molecule more likely to dissolve in the water phase or in the organic solvent phase? It's really a convenient way to purify stuff if you can understand where your product's going to go. Typically the aqueous phase or the organic solvent phase. So we need to know about water solubility. And the first part of that is charge increases polarity and water solubility. Okay, so you're looking for molecules that have charge. And for most sets of molecules, as charge increases polarity, it will also increase water solubility. So here's the question. Which is more water soluble, 1 or 2? Now, the issue with this is it is your responsibility to separate salt. This is a salt because it has oxygen, and more importantly, has a metal. Right? We're not used to seeing metals in organic compounds. Well, that's because in this case you have really Na plus and O minus. What I'm trying to tell you is that it is your responsibility to view that as this. Okay? You have to recognize that this is a salt with the metal counterion, which is sodium plus. And so to assess what this is actually looking like when you dissolve it, it looks like that. You have to separate out the metal and the atom that's, in this case, negative. This is still consistent with this structure here. So really what I'm comparing is the water solubility of 1 and this 2 here. Do you see the challenge? I can give you this structure, but you have to know that it's actually charged. It is charged. It is charged. And what do we say about charged? Charged molecules have increased polarity and water solubility. Okay. So let's, again, this is super important because that, see, it's on a spectrum. Is it ionic bond? Is it a covalent bond? Is it somewhere in between? In solution, you're going to notice you're going to assume that they're ionic and you can separate the two ions. So when dissolved, these two atoms will separate. Your molecule will act as if it's charged, and thus it will be more water soluble. So I'm going to circle this. This is number 2 is more water soluble compared to I or 1. Okay, that's not ionic, right? That's a covalent bond for sure. So you're really looking for the metal. With that being the case, just memorize. These are the +1 metals that you'll see paired up with a negative atom. Lithium, sodium, and potassium. So I could easily put O lithium, O potassium. Now think of this Na plus as a spectator. Okay, it separates, but it really doesn't do any other reaction, and has very little effect on the water solubility of your organic compound. Now this section here hopefully helps you answer this problem, where you have to separate out the metal and show me where the charges are. Okay, so you'll do that with this. This is butyl lithium. Okay, where is the charge once you separate out the lithium? Where's the charge once you separate out the potassium? That's a skill that you want to be very quick with eventually. Last page, page 3. Now, what if your molecules have no formal charges? Okay, well, you're going to look for polar bonds. So the more polar bonds a molecule has, typically the more polar and the more water soluble. But beware, because you could have a polar bond in the molecule, but if you have a lot of non-polar bonds as well, overall the molecule will be considered less polar. Okay, I don't want to use the word non-polar. Typically, when I ask a question, you're comparing two molecules. So I'm going to ask what is more polar and what is less polar. Okay, and so where are these non-polar bonds? They're the carbon-carbon bonds, single, double, or triple. The nonpolar bonds are also the carbon-hydrogen. So if you have a molecule with a lot of these bonds, CC and CH, it may be less polar than another molecule that has less of these carbon-carbon bonds. So we're doing a comparison always, like we're doing down here. Okay. A couple of guidelines. Again, learn how to mark the polar bonds with partial charges. We have partial negative, and we have next to it partial positive. So I listed these. These are the atoms I listed on the first page. And those are electronegative, so automatically put a partial negative. Again, the one exception I can think of is if you have nitrogen attached to nitrogen. Well, there's no imbalance there because they're both nitrogen. But typically, any of these atoms will be bonded to a carbon, most likely. So put your partial negative on these atoms. And then any carbon or hydrogen that's attached to any of these atoms, they are rendered partial positive because the electronegative atom is pulling electrons away from them. And we've seen that, right? It is literally, stuff like this. Okay? There's your negative. Those are your positives around the negative. Number 3, this is something that I think will help you avoid misinterpreting structures. Don't put any partial charges. Do not put any partial charges next to atoms that have a formal plus or minus. And I'll show you an example here. Here it says draw all the formal charges and the partial charges. There's your metal. You have to recognize it. That's your metal counter ion. So in solution, this separates. So we're going to redraw it so we can see the actual charge. If I'm going too fast, go ahead and pause the video. But I need to separate out. How do I know it's negative? Because it was paired up with a metal that's always +1, lithium. Okay? If you want to draw the lone pairs, you can. You don't have to. But you do have to put the charge. Okay. So there's our formal charge. Check. And your partial charges are here. Oxygen's partial negative, and any atom that's attached to it would be a partial positive. Alright, so we're done with molecule I. Look what it says here. Do not put any partial charges next to an atom that has a formal charge. You notice there's nothing here. Okay? Don't put a positive here. Okay? Don't put anything there. Don't put any partial, plus or partial minus. That charge is stating a fact that that atom has one more electron than it typically has. So oxygen typically has, or brings to the party, 6 valence electrons. This one has an extra electron. That's what it's mainly saying. It is true that that oxygen, negative, would be attracted to a positive hydrogen, like an H+. Okay, but it really doesn't do anything to this carbon. Whereas this oxygen is pulling, right? This oxygen is pulling electrons away from these two carbons. So I'm hoping that clarifies or helps you avoid putting anything here. Don't put anything next to an atom that's charged. Okay? Unlike here, where you have to put the partial positives. Understood? Here we have a partial negative oxygen, and here partial positive, partial positive. And then next door, we have a lot. Those are your two partial negatives, and here are your positives next to the partial negatives. I said a lot, definitely more than that, right? So you're going to do this stepwise, like compare any two. Compare these two. This has a lot of polar bonds, and it has a charge. This is probably more water-soluble than this. Okay? Also, this has a lot more carbon-carbon bonds, which adds non-polarity, or makes it more non-polar, less polar. Alright, you can see that? So here, we have lots of CC bonds. CC double, CC single, and also CH. Those are non-polar, right? These are non-polar bonds, which makes the molecule less polar. So this one's more water-soluble. We'll take a look at these two now. Okay, this has more partial charges, and it has less carbon-carbon bonds. I hope you can tell that. So in terms of water solubility, actually, we answered that down here. So this is my analysis for the charges, just answering number 3. In general, charged molecules are more polar and water-soluble than molecules without formal charges. So like comparing these two. Formal charge, no formal charge. But again, you have to beware how many carbon-carbon bonds are there in these molecules. Because if I have a lot of carbon-carbon bonds here, like let's say we have 10 rings, then probably that's going to lower the polarity so much that this becomes less water-soluble or less polar than this one. I'm trying to pick molecules where it's a very clear cut, right? I'm really forcing this to be the least polar. Not only does it have the least number of polar bonds, it has more carbon-carbon bonds. And so we're down to here. We're going to look at this problem 3, and we're going to rank them. And we're going to do it stepwise. So for this one, which is more water-soluble, I, because it has a charge. And 2 is less water-soluble because it has more carbon-carbon bonds. Then we'll take a look at 1 and 3. These two. Okay, they have similar. They have the similar number of carbon bonds. We do have an extra one up here, carbon hydrogen. But this one has charge. Okay, so again, 1 is the winner in this case. And then you can go ahead and compare what we haven't compared 3 and 2. These two over here. Well, yeah. This has more polar bonds and less carbon-carbon bonds. 3 is the winner. Based on that, most water-soluble is 1, followed by 3. Right, 3 is more water-soluble than 2. 2 is the last. Where the greater than symbol is water solubility. Water solubility. Do we have a question on that on your green pre-lab assignment? We sure do. 3 new molecules. Do the formal charges and partial charges first, and then here I'm going to ask you to rank the water solubility, just like we did for these 3. And just for more practice, for number 5, we just jump. You don't have to draw the charges if you don't want to, but can you tell which one's the most water soluble going to the least water soluble out of these 3? Alright, to finish up the green packet, you're going to watch another video that talks about stoichiometry, and we're going to analyze this reaction. But right now, this video helps you answer questions 1 through 5.